Welcome back. This is Professor Carlo again, and we are continuing our discussion of lenses. In the last video, we talked about converging lenses, and when we did that, we introduced these two new equations, which should actually be very familiar. The thin lens equation tells us that 1 over p plus 1 over q equals 1 over f, where p is the object distance, q is the image distance, and f is the focal length. The magnification, of course, is minus q over p, and we get that by analyzing those similar triangles produced by the object and by the image. The sign conventions that we had for mirrors are all exactly the same. So if p is greater than 0, that's a real object, which is everything we've dealt with so far. For q, if q is greater than 0, that's a real image. If q is less than 0, that's a virtual image. And in the case of the converging lens, which we talked about, the focal length is positive by convention. Now, today I wanted to talk about two things. First, I wanted to show you one more cool thing that you can do with a converging lens, and this builds on what we've talked about previously. And then I want to show you diverging lenses. Both of these are rather difficult concepts, so I want to spend a little bit more time explaining both of them. So concept number one today is something that I'll call images at infinity. So photographers often will use the phrase something is at infinity, or someone working on an optical system will say that something is at infinity. Now, I'll explain what that means. So in the previous video, I showed you that if the object distance was greater than f, you produced a real image. A real inverted image on the opposite side of the lens. On the other hand, if the object was closer than f, then it produced a virtual image, an upright image, a virtual image, and on the same side as the lens. What happens if I place the object exactly at f? Well, as always, we can analyze this in two different ways. We can do a ray tracing, and we can also do the mathematics. And maybe for this purpose, I'll do the mathematics first. 1 over p plus 1 over q is equal to 1 over f. Let's let the focal length equal 50 centimeters, and let's place the object at 50 centimeters. I've now got 1 over 50 centimeters plus something equals 1 over 50 centimeters. So in other words, 1 over 50 plus 1 over q equals 1 over 50. Wait, these are the same. I can just subtract that off of both sides. What I get is 1 over q is equal to 0. And this is one of those weird things. What number, if you took 1 divided by it, gives you 0? Well, let's see. 1 over 10 is 0.1. 1 over 100 is 0.01. 1 over a million is 0.000001. 1 over a billion, 1 over a trillion, 1 over a quadrillion. They're getting closer and closer to 0, but they never actually get there. The answer is that q approaches infinity. Think of the biggest number you can possibly think of. 1 divided by that is a really small number, but it's still not 0. If you make an even bigger number than that, 1 over that is still not 0. It's an even smaller number, but it's still not 0. If 1 over q is 0, this tells me that q is at infinity. What does that mean? We know how to deal with q's that are positive. We know how to deal with q's that are negative. How do we deal with a q that's infinity? So here's what we'll do. I'll draw my lens here. There's f on the other side. Let's put in my object, and let's draw some rays. Here is ray number 1, which comes in parallel and goes out. Let's do a little bit more of a careful job here. Comes out parallel and goes like that. Let's draw another ray. This is the one that comes through the center of the lens. Just going to go like that, and it's going to come out this way. And while we're at it, maybe we can put in that famous 2f. Let's do that in another color. And now I'm going to really have to cheat in order to get there, because this is going to miss the lens entirely. But it's still valid. I can do that. And now this ray is going to come out through 2F. And let me draw that. It's going to look like that. Now what I notice, if I look at these three lines, they're parallel to one another. My drawing is not perfect, but these lines are dead parallel. No matter how far I go away, these are not going to converge. So, okay, maybe it's a virtual image. Well, let's extend the lines backwards. I can extend the purple line backwards. I can extend the red line backwards. I can extend the green line backwards. They're parallel. Parallel lines never meet. This never produces an image. There is no place at which the rays of light converge. They are parallel to one another, and they will go all the way out to negative infinity. So now here's the question. If I stood here looking, what do I see? And you might say, well, there's nothing if the light rays don't converge. But maybe I'll ask a different question. If I go outside at night and I look at a really distant star in the sky, I see the rays of light coming from that star, but because that star is so distant, remember the rays of light that it's producing are expanding outwards like that, but if I'm all the way down here, far, far away, by the time those rays get to my eye, they are essentially parallel to one another, because any ray that was slightly off in a different direction, that's not reaching my eye, that's not even reaching our planet. That's hitting Neptune somewhere a billion miles away. The rays of light that hit my eye are dead parallel to one another to very, very high precision. So an image at infinity is very much like looking at a distant star. The rays of light are parallel to one another, so I do see that, but it appears to be very, very far away. Another way to think about it is the human eye can accommodate. If I were to look at this object which is at infinity, my eyes would relax as if I'm looking at something far away. So if I had to look at this and it was close to my eye, I would have to accommodate my lenses, which is something that becomes difficult as you get older. The lenses in your eye have to contract. To look at something that's nearby, I have to focus on it. And when I focus on my finger here, everything in the distance is blurry. But now if I focus on everything in the distance, my finger is blurry. On the other hand, if I were looking at the image of this object, it would be in focus at the same time as the distant objects away from here. So if I focused on objects at the distance, I would see that. Now, an area where this is used is in things like heads-up displays that are used on airplanes, that are used by pilots, or something like Google Glass or virtual reality headsets. What they'll do is they'll aspect the images to infinity, essentially by having your object at the focal point of a lens. That way, when you look at it, you see the distant objects at the same time. So if you're a pilot flying a plane, if you're looking at that heads-up display, which is really just being reflected off the windshield, the text on that display is in focus at the same time as distant objects that you're seeing over on the horizon. So this is kind of an important idea to be aware of. And now that we've settled that, I'm going to move on to the next topic, which is diverging lenses. So this is images at infinity, and images at infinity can also be produced by concave mirrors by putting an object at F, and I encourage you to try doing the ray tracing for that. What you'll find is that you have all of these rays which are emerging from this object, place of the focal point. That will lead to a parallel beam coming out. Where do you see that? A flashlight. When you have a flashlight, it has that little conical reflector. The little light bulb inside produces light in all directions, but it all gets beamed out in the same direction. In other words, it's projected toward infinity. So, diverging lenses. Diverging lenses are sort of shaped like hourglasses. These are lenses which are thinner at the center than they are at the edges. Diverging lenses, by convention, have a focal length which is less than 0, much like a convex mirror. I'm going to do the same thing. I'm going to set up f and 2f on either side. And now we're going to try doing a ray tracing. Let's place an object right around here. Now this is a little tricky. Remember, as I said at the beginning of this video, I'm going to tell you about two tricky concepts. The first one was this image is at infinity. The second one is going to be diverging lenses. We have to think a little bit carefully about how we do this. So our rules for rays are exactly the same as before. I have this red ray which comes in parallel to the optic axis. Now it's going to go out along a line which passes through F. Oh, that's F, right? Wait, the focal length is negative. The focal point that we're interested in is this one right here. So what I'm going to do is I'm going to create a little dotted line like that. That's a line which points from F to the lens. That's the way the beam comes out. That's our principal ray number 1. Principal ray number 2 is going to be one which comes in through the center of the lens and goes out through the center. Fortunately, that one doesn't get affected at all. That's going to stay exactly the same. There is another principal ray, and this is one that comes in through F. So you go, oh, there's F. Not so fast. Focal length is negative. So this is a ray which comes in along a line which looks like that. So here is the incoming ray, which is coming in along a line directing it towards the focal point, and this ray comes out parallel to the optic axis. All right, so far, so good. There is a ray that goes through 2F, so the way that that works is I would draw a line between here and here. That ray would come in to about this point, and then it would be directed out along a line which goes that way, which means it would kind of go out, like that. I'm not going to draw that one, that's pretty complicated. So, the rays of light outside here, these are clearly diverging. If they're diverging, this is not going to produce an image over here. We're not going to get a real image. In fact, we're going to get a virtual image. And the way that we get a virtual image, this is a very important point. Remember this red line here? That red line was only a guide to the eye. I'm going to get rid of that right now. And this line here, I'm going to get rid of that as well. Those were only guides to the eye that we put in order to help us draw the lines. When we're going to determine where the virtual image is located, I'm looking from over here, and remember, I'm taking the refracted rays, not the extension of the incoming rays, the refracted rays, and I'm extending those backwards to see where they meet. So for example, the purple refracted ray, if I were to extend that backwards, it goes like that. The green ray goes in a straight line, so I don't have to worry about that. The red ray, if I were to make that go backwards, it goes to here someplace, and what I see is that these three rays converge right around here. Again, very careful. When we produce the virtual image, it's the extension of the refracted rays. It's not the incoming rays or the incident rays, which is why I don't pay attention to the green or the purple lines here. Those are the incident rays, which mean nothing to the observer over here because they get bent. All that I care about is where the red ray projects backwards, which is to there, where the purple ray projects backwards, which is to there, and where this green ray projects backwards. The green ray happens to go in a straight line, so I don't have to do any extra work. What I see is that those three lines converge there. That's the image. There's the object. So we'll notice from this that this image is virtual. The image is upright, and I will also see that the magnitude of the magnification is less than 1. The image is smaller than the object. We can do the calculation in the same way. 1 over p plus 1 over q equals 1 over f. We can solve for the image location. What we will find, and what we will always find for a diverging lens, is that if I have a real object, it produces a virtual image. It will produce a virtual image. That virtual image will be upright, and its magnification will have a magnitude of less than 1. So for real objects, you will always have this result. You will always have a virtual image, you will always have an upright image, and you will always have a magnification of less than 1. Now, we'll contrast that to the case with converging lenses. Remember, for a converging lens, if I start further than f, if the object is greater than f, I get a real image, which is inverted. For a converging lens, if my object is closer than f, then I do get a virtual image. It is going to be upright, but the magnification is going to be greater than 1. So a little hint here is if I tell you that I have a lens which produces an upright virtual image and the magnification is less than 1, you know that it's a diverging lens. If I tell you that the magnification is greater than 1, then you know that it's a converging lens, if it's a virtual image. And with that, I think I'll bring today's discussion to a close. I wish you good health. I wish that you stay safe, live long, and prosper.